Okay, these are notes starting about limits, and I'm using these for math analysis. If you're taking honors math analysis, then you do well at the end of honors math analysis. You could skip regular calculus and go to AP calculus. If you do that, then you'll need to understand what limits are. These are the notes that I use in AP calculus. A limit has three ways it can be determined. You can determine a limit numerically, analytically, and graphically. I'm going to focus today on numerically, but I first want to just kind of go over what a limit is. A limit is what's happening to a function as you approach a value of x. So I've got a graph here, and let me zoom in so you can see this a little bit better. In this graph here, you can see the function is approaching this vertical asymptote here. It's coming from this vertical asymptote, approaches 0, and turns and goes back down along this vertical asymptote, and it goes along this vertical asymptote and then keeps going towards infinity. So in this case, a limit at the value of -1 does not exist, and a limit at +1 does not exist, because you have these vertical asymptotes. So the definition says if f of x becomes infinitely large or infinitely small as x approaches c from either side, the limit fails to exist. Another time when a limit fails to exist is a situation like this. This is a greatest integer function, so there's these steps along the way. And each integer has a value, and each x between the two integers has a value, but when you get to the next integer, the value jumps up to the next integer. So what's happening is that the limit is not existing at all these integers because something different from the left and something different from the right are happening. So the definition says the limit fails to exist if f of x approaches the limit to c from the right and the left are not the same. So that's what's happening here is I'm coming from the left and I'm coming from the right. The y value is different, so the limit fails to exist. And the last case, which is not as common, is you've got this function here. It's going down, up, and then it's just going back and forth. And as it goes here, it's going back and forth, up and down, and keeps going. But the limit at 0 fails to exist because what's happening is as it's coming closer and closer to 0, this is oscillating back and forth. So the limit fails to exist if f of x oscillates infinitely many times between two numbers as x approaches that number from either side. So those are notes I use in AP Calculus. Now to talk about limits numerically. So like I said, there are three ways to find a limit, and the first way we're going to talk about it is using a table of values, which is referred to as numerical. So what I want to find, how this is read, is the limit as x approaches 3 of 2x plus 7. So if you think about it on a number line, if you're approaching 3, on the left-hand side of 3, you're going to have a 2. On the right-hand side of 3, you're going to have a 4. So we want to know what's happening as I get close to 3 from the left and close to 3 from the right. So I'm going to choose a table of values. And I get to pick my x values. And then I'm going to take those x values and plug them into 2x plus 7. So if I want to get close to 3, I could start here at 2.5. I could go to 2.6, 2.7, 2.8, but I'm not going to do all those. The next one I'm going to use is 2.9. Then I want to get even closer to 3. So I'm going to 2.99. And even closer, and I'm going to go 2.999. And I could keep doing this, keep getting closer, but that's going to show you what I'm trying to show you. Then I'm going to use 3. On the right-hand side of 3, if I want to get close to 3, I could start here at 3.5, 3.4, 3.2, 3.1, but I want to get closer than 3.1, so I'm going to choose 3.001, 3.01, 3.1, and 3.5. And these are getting closer, so if I'm coming from the left, I'm getting closer to 3. If I'm coming from the right, I'm getting closer to 3. And then I'm just going to plug all these values. I'm going to put 2.5 into x. And the quickest way to do this is to use a calculator. So I'm going to go to my y equals, type in the function, which is 2x plus 7. I want to go to the table, but notice the values aren't there that I want. So I want to change my table, and I want to go to my independent variable, and I want to highlight ask and hit enter. Now when I go to my table, you can see there's no x values. It's waiting for me to tell the x values I want it to use. So if I use 2.5 for x, I get a 12. So I can write a 12 here. If I do 2.9, I get 12.8. I'm going to move this to this side so I can see better. Okay, and that would keep happening. So if I type in 2.99, 2.999, 3. So I'm going to have 12.98. I'm going to have 12.998. And at 3, I'm going to have 13. And I would do the same thing on the other side. So I'd have 3.001, 3.01, 3.1, and 3.5. So I missed, oh, I know, I can only have so many. So 3.001, I get 13.002. I can't have this 3.5 yet. I'll get 3.01. I get 13.02. Get a little bit more legible. At 3.1, I get 13.2. And at 3.5, I get 14. So my calculator doesn't let me do a whole list of these. I can only do a few of them, so I just typed over. Now when I come back and look at this, what's happening as x gets closer to 3, so I'm coming in this direction, and coming closer to 3 in this direction. This is getting closer and closer and closer to 13, and this side's getting closer and closer to 13. So the way I'll write this is the limit as x approaches 3 of this function 2x plus 7 is going to equal 13. Not a difficult concept, but it takes a little bit of getting used to. I've chosen 5 examples. This is the first one. Each one of these examples I've chosen are a little bit different. So now I'm going to look at the limit as x approaches -2 of the function x squared minus 4. So once again, a number line will help me. If I have -2 there, -3 is here, and -1 is there. Because remember, you've got 0 here. So I want to get close to -2. So this number here would be -2.5. So when I start my table, I'm going to choose -2.5, and then I'm just going to go ahead and jump to -2.9, -2.99. I'm going to go to negative, oh, I'm sorry, I have that wrong. Let's go back. -2.9 goes that way, so I have -2.1. -2.01 and -2.001. And that's why I put the table or the number line there so I wouldn't make the mistake, and I made the mistake anyways. If I chose -2.9, it's coming this direction. This is -2.4, -2.3, -2.2, -2.1. So I want to get close to -2. And now I have to go on the other side. So this is -1.5. -1.6, 1.7, 1.8, 1.9. So the next one I'm going to have is -1.999, -1.99, -1.9, and I'll do -1.5 just to show you. So now I've already got most of these numbers in my graph, but I'm going to show you once again. So now I want to get the functions could be x squared minus 4. And I'm going to go to my table, and I don't want these same numbers I had before. I'm just hitting delete each time. And I'm getting rid of all those numbers. And I'm going to start with negative 2.5, negative 2.1, negative 2.01, negative 2.001. I'm going to write those numbers down. So 2.25, 0.41, 0.0401, and 0.04. If I plug in a negative 2, I get 0. So I'm going to go back up here. So I've got negative 2, negative 1.999, negative 1.99, negative 1.9. And I have negative 1.5 as my last number on this side. So I've got negative 0.004, negative 0.399, negative 0.39, and negative 1.75. So when I look at this table of values, as I'm getting closer and closer and closer to negative 2, from the left, I'm getting closer and closer to negative 2 from the right. These numbers are positive and they're getting close to 0. These numbers are negatives and they're getting close to 0. So what happens is my limit as x approaches negative 2 of this function x squared minus 4 is going to equal 0. Those first two are pretty easy. Now I'm going to change it up a little bit. This next function is different. I've chosen a rational function here. And what's happening here is if I have the limit as x approaches 0, the rational function, the numerator is x squared plus 3x, and my denominator is x. Well, I've chosen this function on purpose because if I put a 0 in the denominator, I get an undefined function. So if you're looking at 0 on a number line, you have negative 1 on the left and 1 on the right. I want to choose, like this would be negative 0.5 and this would be positive 0.5. I want to get closer and closer to that 0. So I'm going to shorten this up a little bit. My x that I'm going to choose, and I'm just going to write f of x here so I don't have to write the long function out again. I'm going to choose negative 0.1, negative 0.01, negative 0.001. And I'm going to put a 0 here. Then I have a positive 0.001, 0.01, and 0.1. Now that we've done a couple of these, I'm not going to use as many numbers. And I've already got the numbers. I'm not going to use my calculator again. When I put these into the calculator, I get 2.9, 2.99, 2.999. Here, my calculator says there's an error, so I don't have a number. Then I have 3.001, 3.01, and 3.1. This is different from the other ones. There's not a number here. There's an error. But in Algebra 1, that would give me a problem, even in Algebra 2. But when you get to calculus, I don't care what's happening at 0. I want to know what's going on before you get to 0 on either side. So what's happening, this is 2.999, this is 3.001. If I got closer and closer and closer, this value for f of x is going to approach 3. So what happens is my limit as x approaches 0, x squared plus 3x divided by x is going to equal 3. My next example is a little bit different as well. I'm still going to approach 0, so I'm going to use the same numbers that I did the last time. I'm going to look at x as x approaches 0 and f of x. So as x approaches 0, I'm going to use negative 0.1, negative 0.01, negative 0.001. I'm going to put a 0 here, and I'm going to have 0.001, 0.01, and 0.1. When I plug in my calculator negative 0.1 in for x here and x here, the number I'm going to get is going to be negative 29. Next I get negative 299. Then negative 2,999. At 0 I get an error. I get 3,001, 301, and 31. This is different from all the other problems. This is negative. These are larger negatives. These are going towards negative infinity. These are positive numbers, but they're getting larger and larger and larger as you get to 0. So these are going towards positive infinity. So this is going towards negative infinity, which means the function is going down. These are going towards positive infinity, which means the function is going up. Since these are not going in the same direction, not coming close to the same number, the limit fails to exist. So the way this is written is I would have the limit as x approaches 0 of x plus 3 over x does not exist. And most of the time, I'm going to use the abbreviations DNE for does not exist. So it's not possible, it doesn't occur, however you want to say it. My last example, again, is different as well. So now I have as x approaches 1. So when I pick my values, I want to get close to 1. So I'm going to pick 0.9, 0.99, 0.999. And I'm going to put a 1 in there. 1.001, 1.01, and 1.1. And when I get the numbers from my calculator, I get 2.71, 2.9701, 2.997. So now that I see this is 2.7, 2.9, 2.99, this is getting closer and closer to 3. But once again, I get an error right there. I cannot divide by 1. I can't divide by 0, so 1 minus 1 is 0. This side of the limit, what I'm looking at, I get 3.003, 3.0301, and 3.31. So as I'm coming from the left, this is getting closer and closer to 3. As I'm coming from the right, this side is getting closer and closer to 3. At 1, I get an error, but that's okay. Calculus, we don't care about what's happening at 1. So what I would say is the limit as x approaches 1, x cubed minus 1 over x minus 1 is going to equal 3. So the first way I usually teach this is finding a limit numerically. Just means you're going to use numbers. You're going to use a table of values.